In this question, we have a current carrying wire which is placed in external magnetic field, and we need to calculate the force acting on this wire. Now this concept you have already studied in 10th standard, that whenever we have a current carrying conductor and if it is placed in external magnetic field, then there will be some force acting on that current carrying conductor. The reason behind this is the current carrying conductor also starts behaving like a magnet. So whenever there are two magnets close by to each other, obviously there will be some force acting between them. So in 10th standard, they didn't taught you the formula of the force acting on this wire. But in 12th standard, in topic 4.2.3, they have taught you this equation also. So from this equation, you can obtain the value of the force which will be acting on this current carrying wire when it is placed in this external uniform magnetic field. The value of this magnetic field, the current in this wire, and the angle between this wire and the external magnetic field is already given in the question. And by using the equation F is equals to IL cross B, you can obtain the value of force acting on this wire. So if I write this equation in scalar form, I can write it like this: F is equals to ILB sine theta. But this will give me the total force acting on the wire. And I need to calculate the magnetic force per unit length of the wire. So if I want the force per unit length, I need to have the total force divided by the total length. So that I can obtain from this formula. This is the total force and this is the total length. So if I take this L on the other side, then I will have equation somewhat like this: F divided by this L is equals to IB sine theta. Now theta was the angle between the wire and the magnetic field, which is 30, and we know the value of sine 30 is equals to half. So after substituting all these values, the force acting on the wire per unit length is 0.6 Newton per meter. In numerical 4.6, we have a 3 centimeter wire carrying current. It is placed in a solenoid perpendicular to its axis. So suppose this is a solenoid and its axis will be this one. The wire is placed perpendicular to this axis. So I can say, suppose if this is the wire which is placed inside the solenoid and it is perpendicular to this axis of the solenoid. Now they are asking you to calculate the force acting on this wire. This wire already carries a current of 10 ampere, and that's why this wire itself will start behaving like a magnet. And when it is placed inside a current carrying solenoid, obviously current carrying solenoid also behaves as a magnet. So now we'll have two magnets. One is this current carrying solenoid and the another one is this current carrying wire. So again, like in previous example 4.5, we are having two magnets side by side to each other. So there will be some force acting between them. So again, we will be using the formula which we have learned from topic 4.2.3. Force on a current carrying conductor when placed in external magnetic field. So the external magnetic field here will be the magnetic field of this current carrying solenoid. Suppose this is the direction of current in the solenoid. So we'll have some magnetic field of this solenoid, and in that we have placed this current carrying wire. So we have all the values given. Length of this wire is 3 centimeter. We'll be doing the calculations in MKS unit system, so we'll convert it into meter. The value of current through the wire is 10 ampere and the magnetic field of this solenoid is 0.27 Tesla. So by using the formula F is equals to IL cross B, we can obtain the answer. So in scalar form, we can write F is equals to ILB sine theta. Now, while substituting all these values, just see what is the value of theta. In question, it is given that the current carrying wire is placed inside the solenoid perpendicular to its axis. So this is the axis and this is the wire which is placed perpendicular to the axis. So here, theta is equals to 90. and value of sine 90 is equals to 1. So you have to substitute that value over here, and after doing all the calculations, you will obtain the force. It is 8.1 into 10 raised to minus 2 Newton. And suppose if you want to find out the direction of force on this wire, then you will be using Fleming's left hand rule, which you have studied in 10th standard. You have to use your left hand. The pointer finger will show the direction of external magnetic field. The middle finger will be showing the direction of current. Then thumb will show the direction of force acting on the current carrying wire. So you have to align these two, magnetic field and current. Then in whichever direction the thumb points will be the direction of the force acting on the current carrying wire. Now suppose here this is the direction of magnetic field of the solenoid. We know that the magnetic field of the solenoid is similar to that of the bar magnet, and in a bar magnet, or you can say in a solenoid, the direction of magnetic field outside the magnet will be from north pole to the south pole, and inside it will be from south to north. So you can determine north and south of these solenoid in this way. And suppose if you want to find the direction of force on this wire, then see, you have to align the pointer finger along the direction of magnetic field. So inside the solenoid, this is the direction of magnetic field, this way. Now suppose if I assume that the direction of current in this wire is like this, downward direction. So this is the direction of current. So this is magnetic field, this is current, then the thumb shows the direction of force. So you can say force acting on this wire will be in upward direction. Here they didn't ask you about the direction of force, and therefore they have not given you the direction of current, neither in the wire nor in the solenoid. So you won't be able to know the south and north pole. This I was just revising what you have studied in 10th standard. So this direction portion you need not write in exam, as it is not asked in this question.